sound is a longitudinal wave that's caused by the vibration of an object. That object can be a guitar string, it could be the reed in a clarinet, it could be somebody's lips on a trombone, or it could be the skin of a drum. It could be our vocal cords vibrating, but that vibration causes the sound. Now, sound needs a medium to propagate through. What this means is that sound needs some kind of a material. It doesn't exist in a vacuum because there's nothing vibrating. It usually exists in air. We usually hear things in air, and it's the air molecules vibrating back and forth. But it could exist in something like water. So we can hear underwater. It's muffled, but we can still hear. Thinking of some old cowboy movies, a lot of times they'll put their ear to the railroad track, and so they can hear through the railroad track. The railroad track's particles are vibrating back and forth. Now, if we have more than one type of wave, which is usually the case, more than one type of sound wave, they will combine together. The way they combine together is called the superposition principle, which says that the net displacement of a wave at any given point is the sum of the individual wave displacements. Now, sometimes they add together, which we call constructive interference, and sometimes they cancel out, which we call destructive interference. In constructive interference, the crests and the troughs match up with each other. And so what we get is a wave that is twice as big, twice as large of an amplitude. So in constructive interference, it's interference in which individual displacements on the same side of the equilibrium position are added together to form the resultant wave. In other words, the crests match up to give us twice as large of a crest, and the troughs match up to give us twice as large of a trough. But sometimes they don't match up. They are what we call out of phase. And so when they're out of phase, a crest of the first wave matches up with a trough of the second, or a trough of the first wave matches up with a crest of a second. And so they cancel each other out. And we refer to this as destructive interference. This is interference in which individual displacements on opposite sides of the equilibrium position are added together to form the resultant wave. An example of this is noise-reducing headphones. They get a wave coming in, and then they flip it, they make it out of phase, and then send it back out to cancel out the incoming wave. Now, most times, these two waves that interact are not completely in phase or completely out of phase. They're kind of an amalgamation of both. And so here we have two waves that are different, completely different frequencies. And so what happens is sometimes their peaks match up and we get a larger area. Sometimes their troughs match up and we get a lower area. And sometimes a peak and a trough match up and we get pretty much zero sound at that spot. To show an example of this, what we have is a simulation which we can produce a sound. So here we have a nice sinusoidal wave, very mellow sound. But we can add some different waveforms. So if I add a second waveform, what we see is the sum when they combine together. Here we have a peak matching up with a trough. This peak is about a half and the trough is a -1. So the resultant wave is about a -1/2. It's the total of those two amplitudes. Sometimes they combine together as well. Like here we have a half and a half, which gives us about a 1 for an amplitude. And we can add many different types of waveforms, and they just continue to vibrate or add together to give us a very unique sound. And we call this unique sound, this is the tone quality or tone color, but more technically it's called the timbre, which is the unique sound given off by an instrument. We'll talk about that in a little bit. Now, when sound interacts, sometimes it produces a standing wave. This is a wave pattern that results when two waves of the same frequency, same wavelength, and amplitude travel in opposite directions and interfere. So as this wave travels and bounces off of a surface and comes back, it interferes with another wave that is traveling forward. And so this produces a series of points where we get maximum amplitude, which we call antinodes, and points that don't move at all, which are called nodes. So the node is a point in a standing wave that always undergoes complete destructive interference and therefore is stationary. So in the string here, we see certain points don't vibrate back and forth. And a lot of times we demonstrate this with a slinky. And there are certain points that move a maximum displacement. We call those antinodes. Those are points in a standing wave halfway between two nodes at which the largest amplitude occurs. Now, if we just have one antinode and then two nodes on either side, we call this the fundamental frequency. This is the lowest frequency of vibration of a standing wave. It's sometimes referred to as the first harmonic as well. The harmonic series is a series of frequencies that include the fundamental frequency and integral multiples of the fundamental frequency. So what happens is we can also, besides making one antinode, here if we have a vibrating string, we can make two antinodes, which we call the second harmonic. Then we can make three antinodes, which we call the third harmonic, and so on and so forth. And so we see here that for the first harmonic, the wavelength is simply half the wave. Let me try a different color here. The wavelength, or the length of the string, is simply half a wavelength, I should say. The length of the string is half a wavelength. With the second harmonic, when it's tied on 2 points on either end, we see that we have the whole wavelength. And so the wavelength is equal to the length of the string for the second harmonic if it's tied on both ends. And so for the third harmonic, we get 1.5 waves. And so the wavelength is 2/3 of the length of the string. And so we see that the formula is that the wavelength is 2 divided by the harmonic times the length of the wave, or the length of the string, sorry. The speed is the frequency times the wavelength. So the speed of a wave is the frequency times the wavelength. So doing some recalculating, we get that the frequency of a certain harmonic is the number harmonic it is times the speed of the wave divided by 2 times the length. Now, when talking about sound, most of the time we're talking about things like pitch, volume, timbre, which is tone quality, and something referred to as beat frequency. Pitch is how high or low we perceive a sound to be, depending on the frequency of the sound wave itself. So if a sound is high, it has a high frequency, or a high pitch. If the sound is low, it has a low frequency, or a low pitch. To demonstrate this, we see that we have two waves of different frequency. We have a low frequency where the wavelength is longer, and a high frequency where the wavelength is shorter. Remember, frequency is how many waves pass by in a certain amount of time, usually 1 second. It's measured in hertz, which is the number of waves that pass by per second. And so a low frequency is a low pitch, so this would be a low pitch, and a high frequency would be a higher pitch. The next thing is volume, and the volume is how loud we perceive the sound to be, and it depends on the amplitude of the sound wave. And so here we have a certain wave that has a certain amplitude, and so the amount of amplitude is how loud it is. If we decrease that amplitude, it's going to make it a quieter sound. Timbre is the tone quality of a steady musical sound that is the result of a mixture of the harmonics present at different intensities. So trumpets and violins have a different timbre, they have a different tone quality, and it's based on the shape of the wave that they produce. So because they give off different harmonics in the harmonic series, like one instrument might give off a harmonic of 1, 3, and 7. So if we again view this again, we can see if it gives off a 1, a 3, and perhaps a 7, it'll give a certain waveform which gives us a certain sound. But if it gives off different harmonics, like maybe it gives off a 1, a 4, and a 6, it again gives off a different sound, a different tone quality. It sounds different. Now the last thing we want to talk about is something called beat frequency. This is the interference of waves of slightly different frequencies traveling in the same direction, and we perceive as a variation in the loudness. So it gets loud and then quiet, and then loud and then quiet. And so we get this beat frequency, this kind of wah, wah, wah effect. And so if two instruments are slightly out of tune, we get this beat frequency, which is demonstrated here. Here's one sound. Nice sinusoidal wave. And here we have another instrument giving off another sound, just in slightly different in frequency. And so we can hear this wah, wah, wah effect, which is the interference sometimes causing it to be loud, sometimes causing it to be quiet, and we know that they're slightly out of tune. Now, the longer that beat frequency is, the more in tune they are. And the shorter that beat frequency is, the more out of tune they are. So here's some that are really out of tune. And the beat frequency happens more rapidly. If they're more in tune, the beat frequency gets longer in between loud and quiet intervals, and it sometimes comes to a stop if they are perfectly in tune. So when talking about sound, we have pitch, volume, timbre, and beat frequencies produced by different instruments, and they apply to frequency, amplitude, and just the different shapes of the waveform given off due to constructive and destructive interference.